Great. So hello, everybody, and welcome to this week's AFMS seminar. It's a pleasure to have you all here, and it's also a pleasure to introduce our speaker for today, Professor Bruce Sutherland, who is a professor at the University of Alberta. He is jointly appointed to the Department of Physics and the Department of Earth and Atmospheric Science. Bruce's research combines theory, numerical simulations, and laboratory experiments to examine, I think, really exciting phenomena in stratified fluids, and he's going to be talking about some of his work on internal tides today. So please take it away, Bruce.
Thanks a lot, Kat, and thanks a lot for the invitation, the opportunity to speak to the Australian group. I'm going to talk about the superharmonic cascade of internal tides, and that may be jargon to a lot of you. So let me just start off by explaining what I mean by internal tide. First of all, you all know what waves are on the surface of the ocean, and they move up and down due to gravity. But you can also have waves inside the ocean that move up and down to buoyancy when the density of the fluid is decreasing with height. For example, you have warmer water at the surface, colder at depth. So those are called internal waves, and internal tides are internal waves that are effectively generated by the surface tide, what's called the barotropic tide, and they have frequencies on the order, typically half a day is the strongest tides, which are generated by the motion of the moon. Anyway, so that's just a bit of background, and most of my talk will explain what I mean by superharmonic cascade. This work originates from work that was done by a GFD fellow at the Woods Hole summer program, Lois Baker. So in just a few short weeks, she made amazing progress on a problem which resulted in a nice paper in JFM. And this work is really an extension of that. And I'll explain what that extension is as I go along. So let me just get down to motivation. So again, the idea is that you have the surface tide going back and forth. The surface tide is basically moving the whole column of the ocean depth back and forth. And if there's a submarine ridge, that's this tall little mountain here, then that motion pushing the fluid back and forth across that ridge forces this fluid to go up and down. And this is a fluid that is, in the jargon, density stratified. Again, the density is decreasing with height. And when you have that up-down forcing motion launches waves. Now, near the hill, the waves that are generated typically emanate away from that hill as beams. But if you go far enough away, what is left over dominating the motion are what are called low mode tides. And effectively what I'm showing here is the lowest mode, the mode 1 tide, where you effectively have one inflection point in the horizontal velocity field. And these low modes then propagate, and because they're such large scale, typically wavelengths of 100 or so kilometers, they don't dissipate very quickly due to viscosity, even turbulent viscosity. And so one of the questions is, how do these waves ultimately break down, leading to smaller scale motion and ultimately turbulence and mixing? And this nice schematic in this paper by Jody Klimek shows a whole bunch of these processes. Again, you have this in low mode internal tide propagating along. It can ultimately hit the coast, and in hitting the coast, you can have turbulence. Some of those waves may reflect, and then you can have interaction between the incident and the reflecting waves. You can have phenomena such as what's called parametric subharmonic instability. Now it's called triadic resonance instability, same thing. All of these are mechanisms by which the waves can take their energy from large scale, bring them down to smaller scale. So what I'm going to be looking at is a relatively new mechanism by which these waves can take their energy at large scale and bring them to small scale. And that's simply through the self-interaction of the low mode wave with itself, not with another wave, not with some small scale pairs of waves as you'd have in triadic instability. Just all you have is a low mode single wave, and it self-interacts. And if it's large enough amplitude, then you can create smaller horizontal scale disturbances. So that's what I'm going to show you next. Well, before I show that to you, to guide a lot of what I'm going to do, I'm going to be referring to observations that were done southwest of Hawaii at this site here called a far field site. So you have tidal flow over this submarine ridge between these two islands in Hawaii. and they launch a beam both northeast as well as southwest. But southwest, they planted this station and they measured this signal of these waves. So they're measuring the horizontal velocities. These lines indicate isopycnals that are rising up and down. And this is again dominated by a combination of mode 1 and mode 2 disturbances. I'm just going to focus on the mode 1 here. And the question is, how does this single mode evolve nonlinearly due to self-interaction? So here's an early simulation of this circumstance. The background stratification, and this is maybe a bit of jargon you haven't seen it before, this is called the squared buoyancy frequency. N is the buoyancy frequency, which is a measure of the strength of the stratification. How quickly does the background density change with height? And it's somewhat typical as a simple approximation to take this to be an exponentially decaying stratification, strongest stratification close to the surface, and getting weaker as you get down to the abyss of the ocean. So I'm going to do this simulation where I have this exponential stratification. I'm going to have a Coriolis parameter, a measure of the Earth's rotation, which varies from 0 at the equator to being largest at the North and South Pole. I'm going to take it to be a relatively small volume, which is not uncharacteristic of waves generated in the subtropics. And some other estimates of the horizontal wave number, the wave that's being generated, and so on, and a relatively small amplitude. So in this simulation, I'm going to show you, this is one simulation. In the left panel here, I'm showing you two wavelengths of this primary wave, or parent wave as I call it. This is a mode 1 wave. You can see that you have positive flow in the middle here at the surface, negative flow underneath with an inflection point somewhere around minus 0.3 at the total depth. In the right-hand picture, I basically just subtracted out the parent wave, and I'm showing you everything else. Now, you might see these stripes, but that's just an artifact of having made the MPEG, which is crossing things across slides. Effectively, initially, we have nothing in the filtered field. But when I run this simulation, you'll see very quickly that this parent wave excites waves that have half the horizontal wavelength and double the horizontal wave number. You can count 4 crests in the right frame as opposed to only 2 crests in the left. But really what's shocking outside of the fact that that was created is they grow in amplitude, and then these superharmonics decay, and then they grow again. And that was the problem that I put to Lois Baker and asked her, why do we get this beating phenomena where the waves grow and then decay? So that's what I'm going to try to walk you through through a whole bunch of math. And I don't know if 3 in the afternoon is a bad time to have math, but let me tell you, at 11 p.m. in Edmonton, it's not a good time to do math at all, but hopefully you can follow my blithering. Okay, so here's the plan. To set up the state, I'm going to describe everything in terms of a stream function. And so this stream function, which describes the waves, will have an amplitude out front. I've pulled out the frequency. D is at E folding depth of the background stratification, and I'm dividing by the horizontal wave number. This just pulls out the units of the stream function. Alpha then is the non-dimensional amplitude after I pulled those units out. I have a non-dimensional time-dependent amplitude, and that's really what I'm looking for, how this changes in time. I have vertical structure functions that tell me, basically, for mode 1 wave, it describes the structure. And this is for the parent wave, where I have, this will go as e to the I, and that phi represents kx minus omega t. So it has a wave number k, and a frequency omega, which is the same omega out here. Then I'm also adding to that this 2K superharmonic, which is what I showed you in that simulation. So these are all different symbols. It will have a different time-dependent growth and amplitude, a different vertical structure, but importantly, the K and T dependence is 2 phi instead of 1 phi. And then this actually is going to keep on going. We'll go up to 3K just by making this a 3 phi, and so on. So I said it in words. Let me walk you through now in a bit more detail what all these symbols are. So again, phi represents the phase of the parent wave. So effectively, this will have a frequency omega, but for consistent with what I do later on, I might also refer to it as omega 1, which corresponds to the frequency of the 1K wave. This phi hat n is the vertical structure of the mode. Again, that has a wave number of n times k. To get that vertical structure function, this just comes from linear theory. You take the linearized equations and you get an eigenvalue problem that tells you what the vertical structure is. Two z derivatives of this phi hat is equal to all this. Remember, n squared is not necessarily constant. In fact, I'll show you it must be non-constant to get anything interesting. And the eigenvalue of this problem is the associated frequency omega sub n. So again, if I'm dealing with the parent wave, that would be omega sub 1, which for the most part, I'm just calling omega. But I'll also have omega sub 2s, omega sub 3s corresponding to the 2K superharmonic, the 3K superharmonic, and so on. So that's the eigenvalue, which can be solved to give me the vertical structure of each of those superharmonics. Alpha, this is a non-dimensional amplitude, and here I'm defining it as the vertical displacement amplitude, A naught, divided by this E folding depth, D. I could have divided by the total depth of the ocean, but then you would never really have an amplitude of a wave that would go from the surface down to the bottom. So it seemed to be more realistic and intuitive to count the non-dimensional amplitude based on the E folding depth of the stratification. So what we are looking for here is the evolution of the parent wave, the A1 of t, and its superharmonics, these other AN of t's. And it's going to be an initial value problem where we're going to say that the parent wave starts off with this non-dimensional amplitude of 1, and everything else has no amplitude at all. And we're trying to find then a system of equations that will tell us how this AN of t evolves in time. Now, you notice I have a capital T here. I don't have a small t. That's because this capital T is a slow time scale. Compared with the frequency of the motion, the up-down motion of the waves, this slow growth, and as we saw, the slow decay takes place over many periods of the wave. So this epsilon is some measure of that growth and decay of that superharmonic I showed you in that simulation. And what I'm going to show you is it's natural to define that epsilon. This is not clear now, but I'll show it to you. It's natural to define it as the difference in the forcing frequency of the superharmonic by the parent wave, which is at a frequency of 2 omega. That's the self-interaction, the e to the I phi multiplying another e to the I phi in the nonlinear terms gives me an e to the 2 I phi, will force double the frequency. How does that differ from the natural frequency of a wave having the horizontal wave number 2K? They're not necessarily the same. So that's a key parameter, and I want to dive a bit deep into how you, to show you that this epsilon is indeed a small parameter for realistic internal tides. So this is the dispersion relation for this case where the Coriolis parameter is about 0.008 of n naught. This is set up so that one result of this is that when kh goes to 0, these waves basically flatten out and the frequency approaches the value of f. But except for this curvy bit at the bottom, as you go away, it looks more or less straight line-ish. And so now what I want to do is construct what is omega of 2k, that would be the natural frequency of the superharmonic, and what is 2 omega of k, that's just doubling this curve. So that's what these two curves are. The blue is just double twice omega, which would be the forcing frequency of the parent on the 2k superharmonic. Omega sub 2 is the natural frequency of a wave with wave number 2k. And you can see these two curves are very close together. And so when I construct this epsilon, the difference effectively in the squares of those frequencies, you can see it gets to be quite small. And in fact, for realistic internal tides, 100 to a 200 kilometer scale waves have values of kh around 0.2, 0.3. So these would all correspond to epsilon values around 0.1. So it is indeed reasonable to assume that epsilon is small. Now, importantly for what I'm going to dive into, is the case where f gets smaller and smaller and smaller, and I want to go to the limit where f is 0. Effectively, I'm at the equator. So when f is 0, you don't have that cutoff at f anymore, and in fact, the dispersion relation is almost linear. So the dispersion relation is shown in black. If I consider twice that value and compare it with omega of 2k, these curves are almost on top of each other for small k, and you can see the epsilon is very small indeed. That will be very important for what I show you later on to show you that even if the vertical displacement amplitude of the waves is small, in fact, the nonlinearity can be very large as a consequence of epsilon being small. Okay, so all that's just a little sidebar. Let's go back into solving this problem. So these are the equations I'm solving. They're just the envisaged Boussinesq equations. They're fully nonlinear. I don't have viscosity. I don't have any diffusion, but I do have background rotation, of course. And so these are the horizontal momentum equations, the vertical momentum equation, the buoyancy equation, and it's an incompressible fluid. So the plan is we manipulate these equations, putting all the nonlinear terms on one side, put all the linear terms on the other side, and then combine all of those linear terms together to create a single equation for the stream function, the linear operator acting on the stream function on the left-hand side. And it's going to be forced by all of these nonlinear terms that ultimately come from the advection terms in the equations. So this is the key equation. And the plan is if I have a parent wave, and from its stream function, I can work out its velocity, I can work out this zeta, which is its vorticity, work out its buoyancy, and so on. And then I have products of these terms. So again, I'll have e to the I5s multiplying e to the I5s, which is going to create a forcing at e to the 2I5, and hence it's going to try to create something that is a superharmonic. And that's the basic plan of what we're going to do here. So again, the plan is, this is my assumption for what the stream function looks like. It's not just the parent, but it will also have these superharmonics, even though initially the amplitudes of all these superharmonics is 0. And what I want to do is come up with differential equations for A1, A2, and so on. Okay, so we're going to ultimately use those polarizations, plug it into the right-hand side, come up with our forcing, and then we're going to work out the linear response. In fact, what I'm going to do is in reverse. I'm going to come up with an equation for the linear response first, and then I'll get to the nasty algebra, which is looking at the nonlinear forcing. So let's look at the linear response. So we're going to look at the forcing is driving something with a horizontal wave number nk. So, maybe I have a e to the m phi times an e to the L phi, but m plus L adds up to n. So that nonlinear forcing is going to drive something that will be an nk superharmonic. Okay, so that's the setup. And now a few approximations and manipulations. I'm going to use that vertical structure function equation so that where I have two z derivatives acting on the psi n, that's two z derivatives here and here, I will allow me to replace the vertical structure function that just involves, or two derivatives of the vertical structure function, with all this stuff that involves a structure function. And that's where the natural frequency of oscillation of the nk superharmonic comes in. I'm also in this equation, I have time derivatives. Some of those are going to act on the e to the I omega t, but some of them are going to act on the a sub n of t. I'm going to neglect the lowest one, which is order epsilon squared, but I do want a time evolution equation. So I will keep the term that just has an epsilon times a d alpha dt. So that would be this term here. So all that manipulation, sticking it in there, making that substitution, that linear operator on the stream function looks like this. So a bunch of constants out front. Here and now I'm beginning to see a time derivative acting on a sub n. This is approaching the differential equation I want to get. Here now you see this difference in the squared forcing frequency and the squared natural frequency. So now you can begin to see where I come up with this definition for epsilon, which is specifically defined for n equals 2, coming from the very lowest excitation of the parent exciting the 2K superharmonic. Okay, so we have all of this now. I'm going to manipulate this a titch further. This difference in squared frequencies, I kind of want to pull out of the equation, and I want to make use of my definition of epsilon. So I'm going to pull this out. I'm going to define a quantity B sub n, which is 0 if n is 1, 1 if n is 2, and then it's this nasty thing for larger n. But the reason I'm doing that is then all this stuff in that square brackets reduces to a simpler looking differential equation, just a dAn dt, and then an omega times a constant times an an. Everything else has been pulled out, and I've now used my definition of epsilon for the n equals 2 case. Again, that's square of the forcing frequency of the 2K harmonic compared with the natural frequency of the 2K superharmonic. Okay, so we have that. Now let's get back to the forcing. This is now what we're taking. We have that linear operator is driven by forcing. All of these coefficients out front in the linear operator, I'm bringing it to the other side in the nonlinear forcing term. So now I'm really close to where I want to be. I have this differential, this dAn dt plus an an with some stuff out front, a psi hat, and it's equal to this big mess here. So there's one more step to do. We have to use those polarization relations and work out what all those terms are. So again, these are the polarization relations. You tell me what, say, the stream function is. I know what the horizontal velocity is, what the, I'll say, the north-south velocity is. I know what the vertical velocity is. I know the vorticity, and I know the buoyancy. So I can put that into each one of those terms for different indices m and l, such that m and l add up to n, and hence forces this nk superharmonic. So that's the nasty algebra step, which for the most part I'm sweeping under the rug. But there's another step. I want to have an ordinary differential equation, and I can get that because this psi hat n is an orthogonal function. If you look at the decomposition of vertical modes, it's an orthogonal function with a weight, coincidentally, being n squared minus f squared. And so the plan is I multiply both sides of this top equation by this psi hat n. Then I integrate from minus h to 0 from the bottom of the ocean up to the surface, and use the fact that this psi hat is orthogonal. And hence I will then have explicitly my time equation for dAn dt, which is this. So now I have an evolution equation for the amplitude of not just the parent, which is when n equals 1, but the 2K superharmonic and even higher superharmonics. And this evolution equation is driven again by the forcing terms, but after you do all this algebra, it really just simplifies to taking pairs of sums of pairs of these amplitudes of an MK wave and an LK wave times a coupling coefficient. And that EML is where all the nasty stuff is buried. And so, not to make this completely a black box, I'm going to show you what these coefficients are, but it can be daunting. The easy one is if M and L are the same. So imagine the parent wave with M equals 1 self-interacts. So we have a 1-1 interaction. This is the excitation of the 2K superharmonic. And this would be the expression that would give you the coupling coefficient for the excitation of the 2K superharmonic from the parent wave. And the reason I'm elaborating on this is to emphasize this point. In here, this involves an integral of the z derivative of n squared. Remember, that's the background buoyancy frequency squared. And I've been working all through as an example saying n squared is an exponential. If n was a constant, which is a common assumption when working with stratified fluids as a starting point, if n is a constant, then this whole thing is 0, and you do not have a coupling coefficient. And so you cannot excite superharmonic waves unless you have non-uniform stratification. that was something that was more or less overlooked until about 2016. And so this is an important point to emphasize. Although it's nice to assume uniform stratification, you actually can throw away some essential dynamics. And so this is the case where the two subscripts of E are the same, the self-interaction of a wave. In general, this is what EML looks like. It's nasty, but you can work it out. It's just a number in the end. You can quickly work out the vertical structure functions. You can quickly do all these integrals. And so you can quickly find out what all of these constants EML are. So it's gross, but there it is. So let me now get to some results of doing this. Oh, actually, I want to do just a toy example. So let's just look at the self-interaction of the parent to create the 2K superharmonic. Getting back to that original video I showed you where you saw the superharmonics grew and decayed in amplitude. So this is that equation again, and here's our E11. So that's again the parent interacting with itself to create a 2K superharmonic. And I know what the E1 is. So this is a dead simple equation to solve analytically, and this is the answer. So the amplitude of the superharmonic as a function of time would go as 1 minus e to the I omega of the slow time scale. Or if you want to go back into the fast time scale, it's epsilon omega times t. So right away, you see this represents a periodic function, something that will grow and then decay at time. When t is 0, you have a 1 minus 1, so you start off at 0. When t increases, this thing grows as the complex exponential decreases. And then after a period of epsilon omega, or 2 pi over epsilon omega, it'll go back to 0. And so this is what you get in terms of these dashed lines are what are measured from a simulation. The solid lines is what's predicted by the theory in this case. And even down here in blue, that's the horizontal velocity associated with the 2K superharmonic. There's a dashed line and a solid line almost overlapping, showing that you get pretty good agreement here. I want to show you this again, going back to that movie, but with slightly different colors and diagnostics. So again, here is my parent wave up top. Underneath, this is me having subtracted the parent wave, and you're looking at everything else. On the right, this is the diagnostic showing, again, just the horizontal velocity associated with the maximum horizontal velocity associated with the parent wave and associated with the 2K superharmonic. And you'll see lines being drawn as this goes along. So again, you see these superharmonics developing. We only had one wavelength of the parent wave initially, but we have two wavelengths of the superharmonic, and you can see them grow and decay, and it corresponds exactly to the amplitudes and frequencies that are predicted by theory. It's so hard giving a very mathy lecture to people that I can't see personally, so I hope you're still with me. I'm gonna keep along on this path right now. One thing I want to point out here is that the amplitude to which this superharmonic grows is alpha over epsilon. So that would be the amplitude of the parent wave, the non-dimensional amplitude of the parent wave, its vertical displacement divided by the e-folding depth, divided by that epsilon parameter. And in this simulation, these parameters were chosen so that alpha over epsilon was 0.1. However, if epsilon gets small, then this is going to get bigger and bigger. What that means is two things. First of all, if epsilon is small, the period is longer of the beats. So the superharmonics will stay at a larger amplitude for a longer time, and they will grow to a larger amplitude. And that tells you that it's possible for the superharmonic that's been generated to itself excite more superharmonics because they're large enough amplitude and they hang around at large amplitude for a long time. So this is the superharmonic cascade, which is what I'm going to be showing you next. So this, if I didn't truncate the whole system, would be the full system of equations. What I showed you last time was just this set right here, the self-interaction of the parent, creating a 2K superharmonic. If you really wanted to do a closed system here, you would want to look at how the 2K superharmonic is interacting with the parent to influence the parent. That would be, hang on a sec. That would be this case. So if you really want to solve the equations, just looking at the parent and the superharmonic interacting, not just the creation of the superharmonic, but then the interaction back on the parent, you would solve using those two equations. If you wanted, if this alpha or epsilon was larger, then you'd need to include higher order terms. Maybe you only need to go up to the 3K superharmonics. So you would be using this set of 3 equations involving these coupling coefficients. But in general, if alpha or epsilon is really large, you'll need more and more of these terms. And that may seem daunting, but in the end, it is just a coupled set of ordinary differential equations where you know all of these constant coefficients. So it can be computed quite efficiently. So let's go to this Hawaiian motivation here. And I'll say now the reason I'm looking specifically at Hawaii is because this beam was propagating southwest, and you're already somewhat close to the equator. So this beam, as it propagates further and further south, will go into a circumstance where this epsilon is getting smaller and smaller because there's more closer resonant forcing of the natural frequency. So looking at what was measured at the far field site, we have, again, an exponential stratification, but the ocean, in fact, has a surface mix layer. So I'm actually offsetting where the peak of the stratification is by some depth Z0, 100 meters below the surface. But I'm still making it exponential right to the top. If I remove that, make it well mixed to the top, nothing changes. It's a negligible influence on the waves. Okay, so we have the depth of the waves being 5.2 kilometers. The stratification at this 100-meter depth is 0.017. The E folding depth of stratification was measured to be 218. And because we're somewhat in the subtropics, F is smaller than typical values there, about 5 times 10 to the minus 5. The amplitude, the vertical displacement amplitude that was measured at this far field site, it depended if it was a spring or neap tide or somewhere in between, but typically varied between 15 plus or minus 10 meters. And that may seem pretty small, especially compared to 5.2 kilometers depth and perhaps even to 218 meters, but I'll show you that's large enough to get strong nonlinear effects. And so again, they measure the frequency of the waves. They also measured the horizontal wavelength of the waves. So that sets the foundation for the non-dimensional parameters that I'm going to use in the simulations I'll show next. So with all those dimensional parameters, the dimensionless value of F over N naught is 0.003. This is, if you want, the E folding depth of stratification compared to the total depth of the fluid. That's my horizontal wave number compared to the total depth. And this is an intermediate case between the spring and neap tide of when A naught is 15 meters. So that would be 0.003. When you scale that with D instead of the total ocean depth, that corresponds to an alpha of 0.075. So that's pretty, it looks like a small amplitude, but epsilon at that latitude is 0.096. And so that ratio, in fact, is not a very small number. And that tells you that you should expect not just interactions between the parent and 2K superharmonic, but that 2K superharmonic should last long enough to excite successive superharmonics. So that's what the simulation will show you. And again, the fields on the left are showing the horizontal velocity of the parent and the filter case. And over on the right, I'm showing in black, the black line at the top, that's the parent wave amplitude as a function of time. And then there's the 2K superharmonic, and the line below is the 3K superharmonic. In fact, there's more than that, but I just showed those cases. So you'll see as this goes along, you do have the superharmonic being created, but because you have a 3K superharmonic, the wave gets tightened. In fact, there's the phase locking that's happening between all the superharmonics that are being created to create not a scattered pattern of waves, but in fact, a locally coherent wave. Okay, so that was a case where F was 003, and I have my amplitude sort of in the mid range. Let's go to the equator. So this is a case, the amplitude is the same here, but remember near the equator, this epsilon is really small. In fact, this is a case where alpha over epsilon is 21. And so again, I'm showing the same thing. Here I'm showing not just the parent, but the 2K, 3K, and 4K superharmonic. But in fact, I found I had to go up to 20K superharmonics to get convergence in the results. And I'm also, in this case, working in a frame moving with the parent wave phase speed. That's why everything looks stationary. So you can really see the development of this wave superimposed on what would otherwise be a stationary parent wave in the frame moving with the parent wave. So some of you who have looked at nonlinear waves and stuff may be looking at that going, well, that looks like a solitary wave train. I'm not sure that language is familiar with you or not, but solitary wave train are basically hump-shaped waves, nonlinear waves, and a wave train basically has more than one hump. So because of that similarity, I went on to compare these results with shallow water theory that predicts the formation of in solitary wave trains. So there's two ways to do it when you're on the F plane. There's, of course, if you didn't have F, a classic study would be look at the Korteweg-de Vries equation. But back in 1989, this was adapted to include the effect of the Earth's rotation. And that's why it's KdV-F, F denoting the Coriolis parameter. And so this is the adapted Korteweg-de Vries equation. It's basically KdV on the inside of the square brackets here, but now you have to do a di-dx of that, and it's driven by this other term that involves the Coriolis parameter. And all these coefficients, again, involve integrals of the vertical structure function. So that's the modification of the KdV equation on the F plane. And just some comments as far as these coefficients are concerned. If it was a two-layer system, then you can analytically solve for the vertical structure functions and hence analytically find expressions for alpha k and beta k, which I've given here. You don't need to do this, but I'm introducing it for what I'm going to do next. So here we have our alpha k and beta k, which basically depends on the upper layer depth. It depends on the total depth. It depends on, I'll say it's a harmonic mean depth of the upper and lower layer and so on. But basically everything's just in terms of these different depths, and C naught, which is the shallow water speed for these waves. The reason I'm doing this is later on, I have a model which is just a two-layer model, but I want to compare it to my simulations where I have continuous stratification. And so to get there, the plan is I'm going to invert these equations and say, well, let's say I have calculated alpha k and beta k for my continuous stratification. Then I can invert these equations and say, well, here is the equivalent total depth, and here's the equivalent upper layer depth. So this gives me a way to convert from, to compare a two-layer model to something with continuous stratification. Okay, so the reason I did that is for this. There's a second model that is used to predict the evolution of interfacial waves on the F plane. And this is the Mayata, Choi, and Kamasa model. That originally was derived without Coriolis forces, and it was adapted somewhat more recently by Helfrich and Grimshaw to include Coriolis forces. And the plan is basically to define a set of variables that's looking at the difference between the upper and lower layer velocities, looking at volume fluxes in the y direction, the into page direction, and assuming that the fluxes in the x direction are zero. And so the equations you get look like this. It's a lot of manipulation and so on, but these are the equations. So there you go. So this is just a second set of equations that predicts the evolution of interfacial waves of some given initial amplitude. So let me now compare the simulations, as well as my model that has the coupled ordinary differential equations with the predictions of the KdVF and this MCCF equations. So this is what we got from the, actually, I think this is from the numerical, no, this is from the superharmonic coupling. So this is the prediction of the evolution of a single periodic wave at t equals 0. As time goes by, it steepens, 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 and you get, again, this sort of somewhat localized hump-shaped wave. So this is that solitary wave that you saw in that first of the most recent simulations I showed you. So this is what my theory is predicting, and these are what the KdVF and the MCCF equations predict. I have to say the KdVF agrees that there's really good similarities quantitatively as well as qualitatively between the two models. MCCF qualitatively similar, but it's slightly a more narrow wave and slightly larger amplitude at this later time of around 5,000. So qualitatively, they're all good, but the KdVF as well as this ordinary differential equation model both have good quantitative agreement. This case I'm showing you is that case close to Hawaii, corresponding to F being 0.003. And I just want to go to the equator now. The equator, this was that solitary wave train that developed in my model, and you get almost exactly the same thing developing periodic waves, steepening, and then forming successive hump-shaped waves as predicted by the KdVF equation. The MCCF equation, qualitatively good, but it has more waves in the wave train, and again, they're slightly narrower. So you might think, well, what's the point of everything I just did? Because we know the KdVF equation, it did the job. Why bother doing the superharmonic? And I guess if you want to come up with just an efficiency answer, mine is just solving a coupled set of ordinary differential equations. I solve it in MATLAB in about 10 seconds. Whereas the KdVF equation is a partial differential equation involving x and time derivatives. For me, solving it, I think I did it in C, took closer to about 5 minutes. And the MCCF was way more complicated. It took over an hour to solve. So just for efficiency, there's that reason. But I think in terms of getting a different insight into how these solitary waves form, you not just thinking of it in terms of a balance between nonlinearity and dispersion, but seeing it as a superposition of successive superharmonics that are acting in a phase-locked manner to create these coherent structures. I think it just gives different physical insight. So that's it for the talk, although I'm going to just show you one more thing. You might ask, why did I always focus on, say, an e to the I phi, multiplying an e to the I phi to create an e to the 2 I phi? There's a complex conjugate there. I could take the parent, have it interact with itself through the e to the minus I phi, the complex conjugate term, and create an Eulerian flow. So I have done that separately, but that's way more work, well, just no time to show it to you. But I have to say, it's really interesting mathematically. There's a neat singularity you see when you're close to the equator, where all the forcing you see at subtropics disappears. And in fact, you won't get any Eulerian mean flow if you have a perfectly periodic wave. It has to be modulated. So I'm just saying that in words, but I'll just leave you with this movie that is showing a calculation of a horizontally modulated wave. It's a fairly long domain. And you can see that the amplitude of the waves, this is the initial state, the amplitude of the waves is relatively low at one point, and it's largest in the middle and low at the other point. You can think of this looking at the waves as the spring and neap tide evolves, forcing larger amplitude and smaller amplitude. This is done on the F plane. And over here on the right are profiles of the Stokes drift associated with these internal waves, the Eulerian mean flow, which will be a blue line, and the Lagrangian flow, which is the sum of those two. So let me just play and show you what happens. So the Stokes drift is right away, and it's more or less steady. There's some modulation, largely because of the waves and some modification. but the Eulerian mean flow you see oscillates. And this is something that Hasselmann talked about way back in the 70s, early 70s, that when you're driving a fluid like this, the response is to create an oscillation at the inertial frequency. And that's borne out by the theory. And so the neat thing about this is if you say we're looking at particle transport in the ocean, especially if you see, look at all these internal solitary wave trains I'm creating, that means I'm going to get all this forward transport. But if you actually look over the whole cycle, not just the solitary wave train itself, but the space in between, the Eulerian mean flow is going strongly negative and then down to zero. The Lagrangian flow is always going positive and negative. And so, in fact, you would get zero net Lagrangian transport over time. I just want to play that for you one more time if I can, just so you can see what I just talked about. So you can see how the Eulerian flow goes strongly negative, and that takes over the Lagrangian flow. But then the Eulerian flow goes almost to zero, so now it's all Stokes drift, and it's all Eulerian, and then it goes back. So this Lagrangian flow is oscillating back and forth between nearly equal positive and negative values, and hence you get zero net transport over the cycle, say between the spring and neap tide. That was a lot of talking. I hope that you're able to follow at least some of what I talked about. I'm happy to take questions.
Great, so thank you so much, Bruce. That was a fantastic talk. We do have a bit of time for questions. We won't keep Bruce too long because I know it's quite late where you are, but we do have time for some questions. Nicole, you've got your hand up. Go ahead.
Hey, Nicole, long time no see.
Hi, Bruce. Good to see you. Thank you so much for that talk. That was really interesting. And I agree with you that it's quite illuminating in terms of the mechanism, because I think I understand some of the superharmonic stuff a lot better than I previously did. So thank you. My question is, I guess, about how we think about this in space, because your solution, I think, is you know, you were showing your phase-locked solution, but if you were propagating north or south, that solution is changing because your Coriolis parameter is changing. So I guess that's what I was kind of trying to get my head around in terms of KDV versus your solution.
Yeah, that's an excellent question. That's exactly the work of my master's student presently. So we're trying to extend this to include the beta plane.
Okay.
And I see that's not just tweaking a knob, but one thing I said right at the end there, especially regarding the Lagrangian flow, is there's a really weird singularity that occurs right at the equator. When F is zero, all the things that are driving the Eulerian flow here, which is at F, it's at a frequency of F, it's the inertial response. But when F is zero, you don't get that at all. And in fact, you end up getting something quite different, provided you have a horizontally modulated wave. So the reason we're trying to extend this look at beta is I'd like to see the smooth transition from finite F as it approaches the equator to see where these dynamics change. So work in progress. So hopefully year and a half, I'll
let me know. Yeah, thank you.
Hold you to that, Bruce, as well. Year and a half from now.
Well, that's going to be really optimistic. I say the plan is also to look at variable bottom topography, because all of this is just flat bottomed. But I think looking at them shoaling would also be very relevant and interesting.
Oh, I definitely think so.
Very much so.
Oh, good.
I know you're there all the time, Nicole. Yeah.
All right, thanks, Nicole. That was a great question. Anyone else in the audience have a question? Feel free to unmute, or simply you can write it in the chat as well. I have a quick question. So my question was on, you mentioned when you applied your technique to, I think it was the Hawaii observations, there was a little mixed layer there, but you said, look, the presence of the mixed layer doesn't seem to be affecting the results at all. Would there be a case, say, in some different region where the mixed layer was deeper, maybe had more of a presence, that it would have an effect? Or you think that it would never the issue.
Yeah, so I regret that I don't have a slide that actually shows the vertical structure functions. If I did, it would help a lot. But if the vertical structure function looks, it's like a sine wave, a half sine that's squashed towards the surface. If you put in a surface mix layer, all it does is it takes that sine wave and just makes it linear to the surface, but it's already nearly linear. And of course, when you're calculating those coupling coefficients, all you're doing is integrating vertical structure functions. So that's why it has virtually no change. But to follow your good question, I assumed exponential stratification all the way to the bottom of the abyss. And really in the ocean, you should have pairs of exponentials. It's usually a strong exponential decrease down to say 1,000 kilometers. And usually then you have a slightly less rapid decrease going down to the abyss. And so now when you do that change, which is really over, I'll say 4/5 of the depth, you do change the vertical structure functions somewhat more substantially, and that does change the coupling coefficients. So it's something I haven't empirically, I've looked into it to see that that was the case, but that's something I haven't explored.
Thank you for answering my question. Any other questions coming from the audience? So one other quick question, and this is actually on how you're numerically solving this. Like, just what time stepping method are you using? Say for, you mentioned this was all in simulations, but yes, in simulations.
So in the numerical simulations, I time stepped by, I think it was about 100th. Everything's scaled with n naught, so it was basically 0.01 divided by n naught. The nice thing about the ordinary differential equations, I have to kind of get up to that, but the nice thing about the ordinary differential equations is they're all a function of the slow time scale capital T. So I can actually step in small chunks of capital T, but that makes me shoot through time really quickly, if you know what I mean, because I don't have to step at the frequency, at a frequency of omega, I just have a frequency of epsilon omega. Okay. So I can do relatively large time steps to capture the amplitude evolution, the amplitude evolution, yeah.
Okay, yes, all right, that makes sense. Thanks for answering my question. We have a comment from Maddie in the chat. Thanks for a very interesting talk, Bruce. And I'll ask one more.
Thank you.
Thanks, Maddie. I'll just ask one more time if we have any other questions. Any other burning questions? Otherwise, we will let Bruce go, and thank you once again for an excellent talk. And
I think it's beer time for all of you, and it might be a nightcap time for me. Who knows? Okay. Thanks again, Kat, and thanks also, Michelle, for organizing this. Take care.
No worries. Thanks, Bruce. Have a good night. Bye.
Thanks, Bruce.
Bye all.